In this video, we want to talk about integration by parts. Now, integration by parts is an integration technique. And what it's doing is it's trying to undo what was done with the product rule. There is no product rule for integration, but integration by parts will allow us to deal with some integrands that have multiplication of different functions inside of them. So what we're going to do is we're going to learn two different methods of doing integration by parts, or IBP. One of them is the theory-based method, and the second is what's called the tabular method. So the tabular method is faster in general, and it may or may not be in your textbook, but I'll show it to you here. They both work in all cases. It's up to you which one you're more comfortable with. You just have to learn the ins and outs of the two different techniques. So we're going to start with the theoretical formula here. And what we're talking about, of course, is the product rule for derivatives. So let me go ahead and share with you my screen. Now that you can see what I'm seeing, let's go ahead and review what the product rule for differentiation is. Remember, you have two functions, f and g, and h of x is defined to be the product of f times g. So we have this function h, which is the product of two different things. And to find the derivative of it, we take the derivative of the first function multiplied by the second unchanged. Then take the derivative of the second function multiplied by the first unchanged and add the two together. In other words, the derivative of f times g is f prime g plus g prime f. This is the product rule for differentiation. Unfortunately, there's no way to undo the product rule directly in integration, and that's why we need integration by parts. So you're going to have to kind of hang with me for a little while because what we're doing may not make sense to you until we get to the end. So I'm going to start with this definition of the product rule for differentiation. And what I'm going to do is I'm going to integrate both sides with respect to x. So I'm taking the integral of the left side with respect to x. That's why I have the differential dx. And I take the integral of the right side, which is, of course, is the product rule for differentiation, f prime g plus g prime f integrated with respect to dx. Now, on the left side, note that h is a function of x, so h prime is a function of x. So when I undo this, I end up back with h of x up to a constant. Now, why up to a constant? Because the derivative was done first. If there had been some plus 5 or plus 82 in the function, it would have disappeared because the derivative of a constant is 0. And then when I undo the process, well, I can't undo that. I don't know what the constant was. It was gone. And so that's why I get the plus c. And then on the right side, what I've done is I've split the sum of these into the integral, sum of two integrals. So I have the integral of a sum, which becomes the sum of two integrals. Now, we know that we can split integrals across addition and subtraction. Never, ever, ever split an integral across multiplication or division. Doesn't work. Okay, so now what do we have? Well, what is h of x? Well, remember way up here, we defined h of x to be f of x times g of x. So we're going to replace h of x with f of x times g of x plus c. And then we still have the sum of these two integrals, which originally came from the differentiation rule, product rule for differentiation. Now we're going to do some u substitutions. So let's leave the two screens up here so we can see what we've got. I'm going to let f of x be u. So this is going to be a u right here. And over on the far right, that's going to be u as well. Not f prime, but f. Now, what that does mean, though, is if I take the derivative of both sides with respect to x, du dx will become f prime of x. Then I can abuse the notation and swing the differential dx around to the other side so that du becomes f prime of x dx. Now, I do have an f prime of x and dx in the first integral on the right side. So this part right here will become du, but the f of x by itself will become a u. So I have a u on the far left and a u in the integral on the far right, and I've got a du inside the integral that's first on the right side. Now, what about this other part? I'm going to let g of x be some function v. So that means when I take the derivative with respect to x on both sides, I get dv dx is g prime of x. And then again, I abuse the notation, swing the differential to the other side. Again, should we be able to do this? No, it's an operation. It's not a fraction, but it works, and so we do it. That's the genius of Leibniz's notation. So we swing that around and we get dv is equal to g prime of x dx. Now, if we look at the two integrals on the right, we do have a g prime of x dx, which is in the integral on the far right. So now we've got something for all the pieces that are in this equation. So I've got a u here times a v here plus a constant is going to be equal to du, that's the f prime of x dx, times v, or v du would be a better way of saying it. And then I've got f of x, which is u, times g prime of x dx, which is going to be u dv. So now if we make the substitutions, we end up with this. Now, you'll notice that I have dropped the c down here. Why did I drop the c? How am I allowed to drop the c? There are two ways of thinking about it. One is I still have integrals on the right. So the integrals on the right are going to have constants associated with them. So in a sense, I can sort of ball all the plus c's together and just have one plus c at the end. The other way of thinking of it is, well, I want a particular antiderivative, so I just choose the antiderivative on the left to be the one with c equal to 0. You can do that as well. You can think of it either way. It works either way. So now what we're looking at is we've got this f of x times g of x, which becomes u times v. And then the integral of f prime of x g of x dx becomes the integral of v du, right? Where the du is the f prime of x dx and the v is g of x. And then the integral of g prime of x f of x dx becomes u dv, where u is f of x and dv is g prime of x dx. Now, what we want to do next is rearrange the terms. And this, again, this took someone a long time to figure out. This didn't just come to somebody overnight or over a week or probably even over a month. This took time to work this out. We're doing it in like 10 minutes. So give yourself a break if you're like, why would anybody think to do that? Well, they didn't at first. They had to work at it. So what we're going to do now is we're going to rearrange the terms on both sides. And we're actually going to solve for this u dv. So we're going to subtract the integral of v du from both sides. So after we do that, we end up with the integral of u dv equal to uv minus the integral of v du. This is the theoretical formula for integration by parts. That's it in a nutshell right there. This expression that you see right here at the bottom, the integral of u dv is equal to u times v minus the integral of v du. In other words, when we're undoing some product, we're not actually applying it directly to f and g. We're applying it to u and dv, right? So remember, u was f of x and dv was g prime of x dx. So it has that differential loaded into it already. But it is a product, right? We did have a u multiplied by a dv. We did have an f of x multiplied by a g prime of x dx. So we are still undoing a product inside the integrand. And that's what integration by parts is all about. How do we integrate when we have a product in the integrand, something multiplied together? And this is the theoretical formula that will let you do that. That's pretty much it. Now, this is great. You know the theoretical formula, you're set to go, right? No. So what you need to know next is, when do you apply integration by parts? It's great to have a technique, but if you don't know when to use it, when not to use it, it's not so useful. So how do you know you might want to use integration by parts? So one of the key things that gives away that integration by parts is called for is you have multiplication in the integrand. That's necessary. And you have two different types of functions in the integrand. Now, what do I mean by types of functions? I'm talking about the major classes of functions. So we have algebraic functions, which includes all the polynomials, the rational functions, all the ones with radicals and x underneath, and of course, the boring constant functions, right? Your horizontal line, y equal 2. It's technically an algebraic function. It's just super boring, all right? And then we've got logarithmic functions. Logarithmic functions are not algebraic. Algebraic is basically adding, subtracting, multiplying, dividing, raising to a power, and taking radicals. That's not what a logarithm does, right? So a logarithm is the power. So a logarithm is a fundamentally different type of function. Then we have inverse trig functions. These are also fundamentally different from algebraic and logarithmic. These are your arc functions, arc sine of x, arc cosine of x, arc tangent of x, the angle whose tangent is x, all right? So sometimes we write this with the inverse function notation, sine inverse of x, all right? So this is the function that undoes a trig function. These are a different type of function. And then, of course, we have the trig functions themselves, sine, cosine, tangent, secant, cosecant, cotangent, the basic 6. These are not to be confused with the inverse trig functions. So let's say you had an x squared multiplied by x. Well, that's two different types of functions. X squared is algebraic and sine of x is trig. Now we can also have exponential functions. This is another type of function that we've seen quite a bit, and you shouldn't be surprised to see it here. If you have logarithmic functions, then exponentials ought to be there as well. Now, typically we like the base to be e because it's the natural base, right? It has some really sweet properties, such as that its derivative is itself and its integral is itself. Gotta love that. But it could also be something like a constant to a variable power. So 2 to the x or 5 to the x, it could be, right? So that's probably the first giveaway that you need integration by parts. You've got multiplication in the integrand and you have two fundamentally different types of functions in there, all right? Well, what if you don't have that? You don't have two types of functions, you only have one type of function, all right? So this might be a case where you end up with something that you don't otherwise know how to integrate, such as natural log of x with respect to x. So when calculus 1, we sort of left you with this cliffhanger. It probably gave you the formula and said just memorize it, but they didn't actually explain where it comes from. Well, the formula for the integral of natural log of x with respect to x comes from integration by parts. What are you doing? Well, there's only one type of function, natural log, which is the logarithmic function. So you let the other function be a 1. Well, actually, technically, 1 is y equal 1, which is technically a polynomial, so it's technically algebraic. So technically, you do still have two functions of fundamentally different types. You have natural log, and you have a 1. You can do the same thing with inverse trig functions by themselves, all right? So that's basically when you know that you need to use integration by parts. You have two fundamentally different types, or you only have one type, but you don't know how to integrate it, and you let the other type be the algebraic function y equal 1, which of course is just a horizontal line. Now, there are some things that you need to remember when you're applying integration by parts that you don't want to forget. If one of the functions is natural log of x, it's always going to be u. There are no exceptions to this rule. It's always u, period. Don't ask, don't debate it, just accept it and move on, all right? We'll see why it becomes u every time. So remember, we're taking the integral of u dv, and we're getting u times v minus the integral of v du. That's our formula, all right? So remember the formula from up here. This is our formula right here. We've got the integral of u dv equal uv minus the integral of v du. So in here in the integrand, you've got something, all right, natural log, and then it's going to become the u. Everything else then has to be dv. That may include another function and the differential, or just a 1 in the differential, right? Now, here's the key to doing integration by parts. U is generally pretty easy to work with because what we do to U is we take the derivative of it. Well, we can take the derivative of everything just about that we work with now. So that's not a problem. dv, on the other hand, we have to integrate dv. So whatever dv ends up being, it's got to be something you can integrate. If it's not, you're stuck. You can't even do integration by parts. So you've got to be able to integrate that dv. So when you look for it, you typically, if there's natural log of x, it's going to be u. That's a dead giveaway. But really, you focus more on the dv and you look at the integrand and you say, well, what parts of that could I integrate? And you try to take the most complicated piece you can that you know you can integrate. And you let that be dv. And then the rest of it becomes u. All right? You may have to apply integration by parts over and over again. This is not a one shot and we're done kind of deal. Sometimes once is enough. I would say that's relatively rare. We typically do integration by parts multiple times. Do not change the choices of u and dv if you have to repeat integration by parts. If you chose u to be the trig function, don't choose the trig function to be dv next time and swap it out with something else. If you do, you just end up going in this endless circle like a dog chasing its tail and never get anywhere, right? Don't change the choices of u and dv when you have to apply integration by parts more than once. We're going to use a mnemonic device, LIATE, which one of my students nicknamed Liate, so I still call it Liate in his honor. And this is going to help us decide what to use for u. So we'll talk about how that mnemonic device helps us in a minute. Basically, if you're wanting to jump ahead, logarithms, inverse trig, algebraic trig, and exponentials. That's why logs always get to be u. They're first in the list. And exponentials are at the very tail end. They almost never get to be u. In fact, there are a few cases where you can switch the trig and the exponentials. If you have t and e, you could do et or te, and it works either way. But most of the time, you're better off just memorize this mnemonic device and stick with it, right? The trig functions, sine and cosine, multiplied by some other type of function, are going to result in patterns that repeat. Okay, why? Why would they result in a pattern that repeats? Let's imagine that, well, we'll take sine and let it be u. I take the derivative of sine, I get cosine. What if I have to do it again? If I take the derivative of cosine, I get negative sine. Hang on. I just got a multiple of what I started with. I started with sine. I took the derivative twice, and now I've got negative sine, which is just sine times a negative 1. I got a multiple of what I started with. This is a pattern that repeats. So it repeats because the derivative pattern of sine or cosine repeat every 4, right? And actually every 2, you get a multiple of what you started with. And all we need is the multiple. What if it were part of dv? Well, it's the same thing. You're undoing this pattern. You're moving backwards instead of taking the derivative. You're integrating. But you're still going to get a pattern that repeats and comes back to the original every 4 and gives you a multiple of the original every 2 times you do it. And so when we have trig functions involved, we want to stop applying integration by parts when we end up with a multiple of what we first started with, of the original integral. So when we get a multiple of the original integral, not the same, but with a different constant on it, maybe a negative, maybe a negative 2 times, something like that, negative 1/3, positive 1/3, then we'll stop applying integration by parts. Again, don't change the choices of u and dv when repeating integration by parts. This is most often a problem in the previous section. If you change the trig function from being u to being dv, and at first you had it the other way around, you're just going to go in an endless loop and you're never going to get anywhere. right? So don't change those choices. Now, the last thing we need to talk about is if you have a definite integral, what do you do then? Well, you have to plug the limits of integration into all the parts. So remember our formula, the integral of u dv is equal to u times v minus the integral of v du. So we have a u times v. So we will have to plug the limits of integration into u times v minus the integral of v du. So when we integrate that second one, we use the same limits of integration as were in the original. So we're going to be using those limits of integration in every part on the right-hand side. Now let's talk about that mnemonic device, liete, or who gets to be u. We're going to go from the top down or from the left to the right. So you're going to read it the way that we normally do in the English language. And we're going to keep in mind that there are occasions, rare occasions, but there are times when natural log of x actually is a part of both u and dv. Now this is weird, but it can happen if you have more than one natural log being multiplied together inside the integrand. The natural log is still going to be u, but it may also be part of dv. But it doesn't violate the rule. U is still natural log, but dv may also have a natural log in it. What are the rules for this mnemonic device? LIATV. This is ATE. This is who is going to be u. So we're choosing u. All right. Now remember, dv, we want it to be the most complicated factor in the integrand with the differential that we can integrate. This lets us know what u is, which is the other piece inside the integral. So we have natural log is always u. If there's no natural log, then inverse trig functions get to be u. If there's no natural log or no arcs function, then the algebraic function gets to be u. If there's no natural log, no inverse trig, and no algebraic, then trig functions get to be sine, cosine, tangent. And then if it were just exponential, we wouldn't be having this conversation because we wouldn't need it, right? We just use u substitution to integrate it. All right, so let's go through the steps to apply the formula. You have to identify that you need integration by parts. You've either got an integrand that you don't otherwise know how to integrate, natural log, or some kind of inverse trig function, or you have two types of functions, algebraic and natural log, algebraic and inverse trig, exponential and algebraic, trig and exponential. You've got a combination of two types. Then you're going to identify which one's u using the mnemonic device, liete. Then you're going to let everything else in the integrand that's not u, including the differential, be dv. So you need the differential in dv so that you can integrate it, right? You can't integrate without a differential. I know some of you like to leave it off. Not in my class, all right? Nail you to the wall for that one. Then using the selected value of u, we want to compute du by taking the derivative. Remember I said u is not very hard because we take the derivative of u, we can take the derivative of anything. The hard part is integrating. So don't forget the differential when you take the derivative of u, all right? We're going to need that in the integral. Remember the formula, right? uv minus the integral of v du. So du is going to have that differential dx. We're going to abuse the notation and swing it around. We got to have a differential so we can integrate that v du. Then we take the selected value of dv, which was everything that wasn't u, including the differential, and we compute by integrating it. If we can't integrate dv, we're stuck. You'll have to try something a little trickier, right? For u, you've got to be able to integrate dv. If you can't integrate dv, the whole method falls apart, right? You can't even get started. There will be a plus c, but we're going to leave it off to the final integral. In other words, what we're really doing is we're choosing a particular specific antiderivative where the constant is 0. Or you can think of it as, well, I'm going to roll all my plus c's together at the end. right? You can do it that way as well. Then we apply the formula, right? So let's write down the formula again. We have u times v minus the integral of v du. Oh, there it is up above. I didn't even notice. I already had it there. The integral of u dv is equal to that. Now remember that what we really have here between the u and the dv is multiplication. That's what this whole method is about. What do you do when you have multiplication in the integrand? How do you integrate that, right? You've got a product. You can't split it up. Don't go there, right? Really bad, all right? In my class, that's like a 0 out of 10 because that's a major conceptual error. So we have u times v minus the integral of v du. That's why we need that differential in du so that we will be able to integrate it. When we're done integrating, if it's a definite integral, we will integrate every single part with the limits of integration. If it's an indefinite integral, then this last integral here will give us a plus c, which we'll slap on the end and call it good, right? These are the basic steps to applying integration by parts. So now what we want to do is roll up our sleeves, get to work, and actually evaluate some of these. So go grab some paper and come back. All right, hopefully you've got some paper. Now what we want to take a look at is actually integrating an example or 5 or more. So we're looking at this one right here. We have the integral of x natural log of x dx. We have the differential, have to have a differential when we have an integral symbol. They're bookends. One goes with the other. They're like, you can't have one without the other. We have multiplication in here. It is between the initial x and natural log of x. There's no multiplication between ln and the x and the argument. That's not a thing, all right? So what we have is the integral of x times the natural log of x dx. Now, we have two fundamentally different types of functions. X is algebraic. So we want to write that down. X is algebraic, or you can think of it as the A portion of Liete, and natural log of x, of course, is a logarithmic function. So now what we want to do is we want to think about who gets to be u. Well, remember the mnemonic device is Liete. That means natural log of x gets to be u. We're going to take the derivative of that part. That part doesn't ever use the differential. The differential goes with dv, not with u. So we're going to let u be equal to the natural log of x. That means that the dv that comes from the formula is going to have to be everything else that's inside the integrand, including the differential. So I took natural log of x to be u, and that leaves x and dx multiplied together to be dv. Now let's recall our formula that we have right here. So for our formula, we have the integral of u dv, that's times, is equal to u times v minus the integral of v times du. All right, that's our formula, the theoretical formula for integration by parts. So what we want to do now is we want to compute du. So we're going to take the derivative of u and the derivative of natural log, both sides with respect to x. Now, I'm going to write it out longhand this first time, but then after this first time, I'm just going to abuse the notation and roll it all together. What I'm really doing here is taking the derivative with respect to x of both sides. I'm applying the same operation to both sides, so I'm keeping it balanced, so I haven't changed the solutions. This means that I have du dx is equal to 1 over x, right? Remember, the derivative of natural log is 1 over the argument times the derivative of the argument, and the derivative of x is 1. So we have du over dx equals 1 over x. Now I want du right? Because look at my formula. It doesn't have du dx, it has du. So I need to abuse the notation, swing that differential around to the right side. So now I'm going to have du is equal to 1 over x dx. And that was what I was looking for. This is what I need for that formula. So now I've got du. This is the easy side. And what did I do? I took the derivative. All right. Now let's look at the harder side. The harder side is the dv side. And what we want to do here is we want to integrate both sides. So when we integrate both sides, what are we actually ending up with? So now I integrate the dv and I integrate the x dx. So I'm applying the same operation to both sides. I've already got differentials. So when I integrate dv, I get back to v, right? I mean, it's basically integrating 1 dv. So this gives me v, technically plus a constant, right? So what are we thinking of here? Well, I've got this constant there. And on the right, when I integrate the right side, I end up with 1/2 x squared plus another constant. Now, what am I going to do with these c's? They're probably not the same c. I'm going to choose particular antiderivatives. Basically, I'm choosing the ones where the c's are 0. Why? Because in my formula, I need v. So I don't want to include the c's because I know that the formula still has an integral in it. I'm going to get an plus c at the end. So I don't need to worry about the c. So I choose particular antiderivatives, namely the ones where each of these c's is 0. So then I define my v to be equal to 1/2 x squared. And again, you can either think of it as choosing the specific antiderivative or c on each side at 0, or you can think of it as rolling all the c's in together at the end. Now, do I have what I need to apply the formula? Yes, I do. U is natural log of x, dv is x dx, and the formula is going to be uv minus the integral of v du. So let's write that down. We have the integral of u dv equal to uv minus the integral of v du. So what I had here essentially was the integral of x, natural log of x, dx, where this part was u, and the x dx was the dv. Then I'm going to take u times v. Notice this is the upper left multiplied by the lower right. We're going to see this pattern coming up in the tabular form. So upper left times lower right, that's u times v. So we're really, in essence, taking these two and multiplying together. So I have, and I'm going to write them in the reverse order because I like to have natural log at the back. So I have 1/2 x squared, that's v, and then times the natural log of x, that's u. So I wrote vu instead of uv. It's commutative, I know you know that. All right, minus the integral of v du. So now what I need to do is take the integral of v times du. Notice that du has this differential because we abused the notation, and that will allow me to do that integral. So the minus is part of the formula. Remember that we rearranged terms to solve for u, the integral of u dv. So this gives me 1/2 x squared, that's v, times 1 over x dx. Now, let's go ahead and complete this by integrating this integral that's on the far right. First, I need to do a little bit of algebra, right? I've got an x squared and division by x. So the first term stays the same. I get 1/2 x squared, natural log of x following along, minus, well, I could pull that 1/2 out, right? It's a constant, it's not going to affect the value of the integral. And this will leave me with the integral of x dx, and I can integrate that. So when I integrate that, what am I going to end up with? Well, another x squared divided by 2, right? So I get another 1/2 x squared. So this basically gives me 1/2 x squared natural log of x, following down from uv, minus 1/2 times another x squared over 2 plus a constant. That constant comes in because the original integral was indefinite. And so this one is indefinite. And when you take an indefinite integral, you only get the answer up to a constant, right? You're looking for an antiderivative function. So you only get it up to a constant. Now, if we simplify this a little bit more and distribute the negative 1/2, we get 1/2 x squared natural log of x minus 1/4 x squared. And then what about this minus 1/2 c? Well, negative 1/2 times a constant is still a constant, not the same constant, but we can still call it plus c or plus k, whatever floats your boat. And now we're done, right? This is our answer, and we're essentially done with this problem. Box it up, and we can move on to the next problem. Okay, let's move a little faster on this next one. This one is a definite integral. We have limits of integration from x equals 0 to x equal 2. We know they're x values because the differential is dx. And we have two different types of functions being multiplied together in the integrand. Definite giveaway for integration by parts. X squared is algebraic, e to the 3x is exponential. So we're going to come over here. We're going to write down, oops, I should use a better color than that. That won't show up too well. Let's use blue. X squared is algebraic, which is the A level. And e to the 3x is exponential, which is the E level, which brings up the back. So guess who gets to be u? Well, x squared gets to be u this time. Remember again, your mnemonic device, liete. So we have the A level and the E level. So A level gets to be u. Whoever's higher or first, left to right, gets to be u. So my u is x squared. And that means that my dv has to be everything else inside the integrand, including the differential. So my dv this time becomes e to the 3x dx. We're going to focus on u first. Remember what we do. We take the derivative of both sides with respect to the original differential, which is dx. And so then I get du dx equals 2x. And then I abuse the notation. Let me go ahead and write that down. So I get du dx equals 2x. So du equals 2x dx. Excuse me. Now, that completes the u side, which is the derivative side. Now we need to find v. Remember that when we integrate, we're going to choose the constants to be 0. We want specific antiderivatives, the easiest ones we can take, where c is 0. Now, how do you integrate something like this? So again, what we're going to do is we're going to put integral symbols in front of each side. And then we're back to calculus 1, where we need to do a u substitution. I've already got a u, so to not confuse you, I'm going to call it omega, or w if you prefer w. It's not going to look the same. So we have w, or omega, equal to 3x, all right? Then I take the derivative of omega with respect to x, and I get the derivative of 3x, which is 3. Abuse the notation, swing that dx around. We really like to abuse notation, don't we? Yeah, mathematicians are big on abuse of notation. So we get 3 dx, but we don't want to abuse it more than we have to. We have to abuse it here to make this notation work out right. So we get this 3 dx, solve for dx by dividing both sides by 3, and dx becomes d omega over 3. Okay, now we can go back to our original integral. We have the integral of dv equal to e to the u, or omega, I keep wanting to say u, e to the omega, and dx becomes d omega over 3. So the 1/3 is a constant. It can come to the front of the integral, and we get the integral of e to the omega d omega, which is just e to the omega. So what does that give us? V plus a c, which we choose to be 0, equal to e to the omega with a 1/3 on it plus a constant which we choose to be 0, right? So basically we have v equal 1/3 e to the 3x, right? Going back to the original. Okay, now again, I said to keep in mind that when you do this process, and this is leading us ahead a little bit, I don't even know if I can get that all on there, to the tabular method, we're going to take the upper left and multiply by the lower right, one row down technically. This is all one row, believe it or not. All right, you start with dv and then you get v. That's the next row. So we take u times v minus the integral of the product of the bottom row, which is v times du. So now we're going to write our formula over here. Maybe I should put it in dark colors. So we have the integral of u dv is equal to u times v minus the integral of v du. So now we have the integral from 0 to 2 of x squared e to the 3x dx is equal to u, which is x squared, times v, which is 1/3 e to the 3x. So I get 1/3 x squared e to the 3x, and I need to evaluate that between 0 and 2. Remember I said that the definite integral, every piece, each term gets evaluated at those limits of integration. So this is our uv part, evaluated between 0 and 2. Now I need to add the integral of the bottom row, which is minus the integral of v, which is 1/3 e to the 3x times du. So I have 1/3 e to the 3x times 2x dx, right? So now I can do a little bit of simplification here. So I can go ahead and evaluate the first term. So go ahead and do that in your head real fast. See what you come up with. See if you get what I get, right? So we will basically evaluate that coming down here. So pause the video for a second, work that out, and then we'll take a look at that integral, which is going to need a little more work. Okay, let's compare and see what we got. For this first part here, I basically end up with 4/3 e to the 6th. So that's what I have here, 4/3 e to the 6th. And for this second part, I have the integral of minus 2/3 x e to the 3x dx. Now, hold everything. Isn't this an algebraic multiplied by an exponential? Yes, it is. So in order to integrate this, what am I going to have to use? Yep, you're going to have to use integration by parts. Pause the video, work out the integration by parts, and turn it back on, and let's compare our answers. I'll write mine in a different color, so hopefully it'll pop out for you. Okay, let's see where we left off. So we've gotten down to this part right here, and we noticed that our integration by parts led to an integral, which again needed integration by parts. So what we can do here is we can do the integration by parts again. But this time we have a new u and a new dv. So when we split this one up right here, what we're looking at is this work over here in this pink color. So we have the integral of x e to the 3x dx. I took the minus 2/3 constant factor and just pulled it out. I'll multiply by that minus 2/3 in a minute, because I know I've got 4/3 e to the 6th minus this 2/3 times whatever that integral turns out to be. So let's do the integral. Again, I have algebraic and I have exponential. So my algebraic becomes u, so u is x. My d of dv is actually the same thing it was last time. It's e to the 3x dx. Don't change what gets to be u and dv. If you do, you're just like a dog chasing its tail. You never get anywhere. When we take the derivative of u with respect to x and the derivative of x with respect to x, we get du dx is equal to 1. Then we abuse notation. Du is dx. On the right side, we integrate using u substitution, but you've already done it once. You don't need to reintegrate it again. You've done it. Just borrow the result. Again, we had a v plus c, but we're choosing the particular antiderivative where the v's turn out to be zeros. The c's turn out to be zeros, rather. So we get this 1/3 e to the 3x. Then we apply the formula, u times v, upper left times lower right. So we have 1/3 x e to the 3x, evaluate between 0 and 2, minus the integral of the bottom row, v times du, 1/3 e to the 3x dx. Well, this time, hallelujah, finally, we got something here in the integral that we can just integrate. Why? Well, because we can take this 1/3 out, and it just becomes the integral of e to the 3x again, which I've now done twice, and this will be my third time in the same problem. So this 1/3 is this 1/3, and this 1/3 comes from u substitution on the e to the 3x. And don't forget, we have to evaluate between 0 and 2. This is a definite integral, so we need to keep it definitely the same. So we evaluate our two terms here between 0 and 2, work out the algebra. If you need to work out the algebra, pause the video and catch up. When we're done, we end up with this result down here. This is what that original integral of x e to the 3x dx is equal to. We need to take this and multiply it by the negative 2/3 that was on the outside of the integral up here. So now we're going to take this and we're going to substitute it in, which you can see I did down here in black. And when we're done, we end up with 3 terms that are all e to the 6th term. So don't forget to combine your like terms and add the fractions 4/3 minus 4/9 plus 2/27 to come up with 26/27 e to the 6th. Oops, and I have a sign error somewhere. I think I must have a sign error down here. It should be plus 2/27, or I've messed up a sign somewhere else. So I'll leave it to you to figure out which one is incorrect, but one of these has got a sign error in it. All right. My guess is, based on what I see here, aha, it's right here. Does everybody catch it? It's over here. I had minus 1/9 times e to the 6th minus e to the 0. E to the 0 is 1. A negative times a negative, that should be a plus 1/9 right there. So if that's a plus 1/9, then this becomes a plus 1/9, and that would make this a minus 2/27, and the answer in blue is correct. In the next video, we'll talk about how to do tabular integration by parts.